Hello and welcome to the CryptoSecEd channel. Today I'm going to look at a couple of Python scripts I've developed, available on GitHub. I developed these Python scripts to help explain some of the basic concepts behind blockchains. So we're going to be looking at some very simplified version of what a blockchain is that we can build together with a small collection of Python scripts. So looking at each of the different fundamental concepts in turn. So what I like about the blockchain is that it is public, it is available. You can read the white paper by Satoshi. You can look at all the internals. The modern banking system is hugely complicated. Lots of different components and systems and organizations. Lots of proprietary technology included there as well. So it's very difficult to analyze. But from an educator and research point of view, if you want to understand the blockchain, it's all well documented. There's code available, all easy to understand and to explore and to play around with yourself. So let's get started. First code here, C1 small hash, is a Python script. We've got one function, gen hash. It's just a convenient way to calculate the hash of a string using SHA-256. And it returns specifically the hex representation of the hash. So we're not getting binary, we're just getting the hex directly. So that's something we're going to use in our main body of our code. What we have here is an infinite loop. We're going to generate a random hash, a hash of a random value, which is generated just picking a random integer within this range. So very large random number, we're hashing it. We're going to store that hash as the current hash. And then every time we subsequently go through this loop, we're going to check, have we found a new hash that is less than the current lowest hash. So we're repeatedly trying to find smaller and smaller hashes. If we do, then we're going to print out various details, including what the random value was, how many times we had to check, how many hashes we attempted to count to hash before we got this new lower hash, and how much time has elapsed in total. So if we run this code, we can see it in action. And what happens is we very quickly get several hashes immediately. We've just got 9 of them instantly, and now it's starting to take a little longer. So you can see it's a very, very small fraction of seconds in between each occurrence, and then suddenly a huge jump up to taking between 0.2 seconds and 0.17 seconds to get the next one. That's quite a large gap. So you can see all the different hashes, and we can see looking at the hashes themselves, they can getting smaller and smaller. We're getting more and more zeros at the start. So they all come very quickly at the start, but then slower as time goes on. And if I run it again, it starts again from scratch. You can see again, we get lots of hashes at the start. Then as these start to get smaller and smaller, it takes longer time to get the next one. So this is demonstrating some of the work that goes behind a blockchain, specifically proof-of-work blockchains. The task of finding a input to a hash function that has an output of a particular format, specifically with lots of zeros at the start. It's a small hash. There is a brute force way to find it. You can just keep on trying random values. You could be iterating here in sequence or randomly. It doesn't matter. There's no shortcut. If I only know in advance that this is the hash I want, there is no known way to generate an input that will hash to that value, but taking any value and calculating its hashes is quite quick. So we're performing a lot of operations here, and we're getting smaller and smaller hashes, and we have an idea roughly how long it takes to get hashes of a particular size. Okay, so that's lets us know a little bit more about hashes. This second program, C2 fixed diff, instead sets a fixed target difficulty, the challenge, and we're looking at, again, going through a random infinite while loop, testing different values, seeing if any of them hash to below this particular challenge. So in this case, the challenge starts with 3 zeros, 0, 0, 0, F, and then the rest is just as many Fs as we want. So the scenario we're using this function here is, what if we wanted, rather than increasingly long time in between finding these hashes, what if we wanted them to occur at roughly the same rate? So suppose we had a target interval, let's say it's 2 seconds. How would we modify this challenge to make sure the hashes were roughly occurring at that rate? So if I clear the screen and try to run this C2, you can see this is happening very, very quickly. Lots of hashes are being found that are lower than the target. You can see all of these start with 3 zeros, and the rest of the characters in the hash can be anything they want. We need to have 3 zeros to be lower than this given challenge. So if I naively just change the challenge by removing a 0 to that, and then if I run it again, this is actually worse. We're getting more and more hashes in a very short period of time. If I increase this quite a lot and try again, then we'll find actually we'll be waiting for quite a while before we get any hashes. So if our desire is to get hashes every 2 seconds, then obviously the challenge is too difficult at this point. So let's take a few of these zeros away. Let's see how this works. Okay, so this is a little better. After 4 seconds, we have 30 hashes. Again, it is a little too easy. We want to make it a little bit more challenging. And let's see how this works. So we've got 1 after 1 second, 2 after 6 seconds. We've got quite a lot there. So again, it's never going to be precise. It seems to be running slower than 1 every second, but it's not quite 1 every 2 seconds. Well, it's actually seems to be, we got 16 after just under 30 seconds, so we can tweak it a little bit. So if we change this to say B, that will make it a little bit more challenging. So you can, if you add a 0, that makes it much more challenging. You're basically increasing the difficulty by a factor of 16 for every 0 you add. You subtract a 0, you make it easier by a factor of 16 as you change this hex value. Each change you make in either direction will change it by a factor of 2. So I think this is a little too challenging, a little bit slowly here, not quite every 2 seconds. So let's say D, see how that works. Okay, this seems to be roughly around the area, approximately the challenge we're looking for. So if you're running this code on your own machine, you might notice that for any challenge you specify, you might be getting different kind of speeds. They might be running faster, might be running slower than my machine here. I'm running on a fairly modest laptop. This all depends on your hardware, how fast your device can calculate hashes. If you're running a much more powerful machine, then you would need a longer challenge, lower value here for this character, or maybe possibly more zeros. If you're running on a constraint device, then you might need a smaller challenge to get it to producing values every 2 seconds. How this relates to the Bitcoin network is that the network is designed to ensure that blocks occur roughly every 10 minutes. So if there is a stable amount of computing power in the Bitcoin network, if all the miners in the world that are mining Bitcoin, if that amount of computing power is known and relatively stable, then there is a particular challenge that needs to be set in order to ensure that with all these miners furiously trying to find hashes that are lower than a particular challenge, they are going to be successful among the whole network roughly every 10 minutes. And if you look at any block explorer and look at any of the recent Bitcoin blocks, sorry, here we go, latest block, and if you see the challenge hash, sorry, let's look at a slightly different block. So we look at the hash of the most recent block. We can see the hash here, and there's considerable number of leading zeros. So this is a hash that has been produced from the result of a significant amount of computing power to find that hash. And again, comparing my meager laptop to Bitcoin miners isn't a direct comparison because there's so much dedicated hardware that's specially built for Bitcoin mining, but still we can get an idea of just how much effort is going into the mining process of the Bitcoin network. Okay, so we have now this idea of proof of work. You can set a challenge, you can search for different inputs to find a hash that will produce a value below that challenge. We know how to tailor that difficulty to get roughly the issuance rate of successful efforts if we know the computing power. This is the proof of work that helps secure the blockchain, but this is only the start. Okay, so we're going to try to create our own little demo blockchain. We need to have transactions. So we assume we have a set of 5 participants. We just need a function to generate some test random transactions. So I've got a little function here, picks 2 random entries from a list. So we're assuming we've got these 5 participants in our blockchain, and we're just going to generate a random number between 1 and 100 to say first person is sending 100 units to the second person. So very simple code. If you run this, you'll see picks 2 members of the group, David and Bob, and it's saying David wants to pay 67 units to Bob. And again, you get a different pair, different amount, and so on. So this lets us generate some data we can put in our blockchain. Okay, very quickly, the last entry I have in this collection, the last script I'm going to talk about in this video is the generate hash chain. So let me run this first so you can see what's happening. 64 generate hash string. So this is a secure chat. All text will be entered into a verifiably secure ledger. So I'm going to type first message, second message, test test last message. And if I want to quit, I just type in N. So what's happened is that's produced a log file. Here we go. So we can see all the entries here are starting with hashes here. And we're not just taking hashes of the values here, because if we were, then these values would be similar, because we've got 3 repetitions of the same message. What's happening instead is we're taking a hash of the previous line and then hashing that and adding that to the log. So if I bring up Ubuntu, so I've got a Ubuntu terminal here that will help me calculate some hashes. So if I run SHA-256-SUM, copy the whole of the first line, paste it in, add a new line, we can see that hash that's produced, that is what's in the first line, the second line of the log. You can see both of those, E61BB, E61BB, 2926B, 2926B. If again try it with the second line, 556999 and 609CDEB. If I try any of these as well, the same thing is going to work. 599C, 599C, BCD4B, BCD4B. So what's happening is as messages are being added to the log, the previous line is being hashed, and that's being appended first. So when I added this message here, it calculated the hash of the previous line, including the previous hash, and generating this hash here. So what benefit this provides is if any single character is changed, either in the previous messages or in any of the previous hashes, then that will be possible to verify by checking these hashes. If I delete a line, that's going to be noticed as well, because of the chain is broken. So obviously copying and pasting hashes is very awkward, very tedious. That's not very useful. What we want instead is a way to verify the hash chain is correct. So in the next video, I'll go through that, and then we'll start putting these things together to show how to use them to generate a very simple proto blockchain.